This video is going to cover how to pass the differentiation standard. It won't go into the more difficult questions, but it will focus on the range of questions that could be asked to achieved. Right, the things we're going to cover in this video. First, we're going to look at revision. We're going to do some differentiation for polynomials, stuff you've maybe done before. Then we'll get onto the chain rule. The chain rule is the main rule for this topic, followed by the product rule and the quotient rule. After that, we'll look at how to find turning points. We'll also look at identifying if they're a maximum or a minimum, and a brief look at second derivatives, even though this isn't necessarily required. Last, we'll look at finding the equation of a tangent or a normal line. In the description for this video, I'll link a document with every achieved question only from 2013 until 2021. And at the end of every section, I'll post a list of all the questions from that document that match the skill that has just been covered, so you can try them before you move on to the next skill. Right, let's get into it. Differentiating polynomials. The most basic form will look like this: 7x to the power of 4. To differentiate it, y dash, also known as dy dx. We can do this by bringing the power out to the front. So here it goes at the front, 4 times, and then we reduce the power by 1, so that will go down to a 3. So that can be written simply as x to the power of 3, 28 at the front. So the general rule for this is if you have ax to the power of n, then the derivative y dash, y prime, n times a x to the power of n minus 1. Let's try another example. Y is equal to this, different parts. You can do all these parts separately as well. Alright, so y dash, the derivative, will therefore be equal to 6 times 5, which is 30, x, power drops by 1, 4 times 3 is 12, power drops by 1, 3 times a half is 3 over 2, power drops by 1, and so on. We don't need to write this power of 1. X to the power of 0, we don't need to write that either. We can just leave that as 6, and a constant, a number like 11, will just disappear. Right, what about if we have a root, the nth root, for example? Let's try one where we've got the square root. If we want to differentiate it, the first thing we have to do is write this a different way. So if we think of it as the second root, we can also write that as power of a half. This is much easier to differentiate. The power goes to the front, and then we reduce the power by 1. Written simply, that would be a half x to the power of negative a half. Here's another example. First thing we need to do, we write it again as a power of a half. The derivative will therefore be a half times 5 x, and the power will drop by 1. So 5 over 2 x to the power of negative a half. This works for any root though, not just the square root. Let's try the fourth root. First of all, we'll write it as 1 over 4 as the power, then that power goes to the front. We have to reduce that by 1. Now a quarter minus 1, how do we deal with that? So we could write 1 as 4 quarters. And then we've just got 1 quarter minus 4 quarters, and that's negative 3 over 4. Slightly trickier example. The third root of x to the power of 5. Step 1 remains the same. Let's just write it as power of a third. You just have to remember this rule about multiplying exponents. So therefore it's going to be 5 times a third, which we can write as 5 over 3. Right, let's differentiate it now. Power goes to the front. We reduce that power by 1. 5/3 minus 1 is the same as 5/3 minus 3/3. Here it is. That'll leave us with 2/3, so that can be our new power. Okay, here's one for you to try. Can you differentiate this? Give it a pause and see how you go. Right, here's the answer. If we differentiate, the power goes to the front, just like before, drops down by 1. And remember, we want to write this as 4/5 instead of 5th root. Power goes to the front. 4/5 minus 1 is 4/5 minus 5/5. That will leave us with negative 1/5 as our power. How do we deal with it when x is on the bottom of a fraction? For example, 1/x². There's a rule that says you can write this as a negative power. So if we do this, it'll make things a lot easier. So here we go. Power goes to the front, and we reduce that power by 1. Now don't forget, -2 minus 1 goes further negative, so it's going to be -3. Another example. Write the power up the top first of all. -5 times -4, and the power reduces by 1, so it goes down to -5. Right, have a go at this one. Pause the video and see how you go. Okay. Power goes to the front. Just like always, we're going to write the power at the top, x to the power of -5. And don't forget we can write x to the power of 7 inside the square root as x to the power of 7/2. Power goes to the front. We reduce that power by 1, which is the same as 2/2. That's going to leave us with this. Just a reminder, that's our rule for polynomials. This is our rule for dealing polynomials with a fraction. And of course, if the power is on the bottom of a fraction, we can move it to the top by making it a negative. So using these 3 rules together, this is how you can differentiate polynomials. Right, let's get into the chain rule. This is the first new rule for this topic. It is also the main rule. You'll be doing the chain rule every single time. In fact, you have been so far, you just didn't realize it. Here it is from the formula sheet. But we're going to think about it as being a function inside another function. So here we've got the outside function, which is the yellow bit. That's to the power of 3, and the inside function, which is the purple bit, which is x² plus 7x. We could, of course, write this out as one big expanded thing, but that's going to take forever and it will get boring. We don't need to do this. So instead, we're going to think about the inside function as its own thing, and the outside function as its own thing as well. We're going to call them f and g. Right, to operate this, we're going to differentiate both bits. Now, how do you differentiate this? Well, first of all, you have to differentiate the outside bit. Only the outside bit. You're going to leave the inside bit the same, and then you'll multiply it by the derivative of the inside bit. Right, that's written as f prime g times g prime. So just to differentiate the outside bit, what was f? F is this thing in the middle to the power of 3. So if we differentiate it, the power goes to the front, and the power reduces by 1. G, x² plus 7x. Stays the same. Right, we'll do the same thing for g, and its derivative is just 2x plus 7. Now we just have to multiply these together. So the derivative of this whole thing is going to be f prime, which is 3g to the power of 2, times g prime, which is 2x plus 7, all in a bracket, because we have to multiply by the whole thing. G was just a name we gave it, so we have to write it back in properly, so it's going to be 3 brackets, the same thing in the brackets, multiplied by the derivative of the brackets. Right, let's look at another example. So let's differentiate this. Once again, we have to identify what is the inside bit. Usually it's in the brackets. The outside bit is going to be this. The 5 will go to the front, reduce the power by 1. And next we're going to multiply by the derivative of the inside bit. Put that in brackets too. There we go. So that's the chain rule written quickly. Okay, here's a further example. Remember what we can do with power on the bottom. We can write it first as 6. Here's the bracket, and make the power a -4. So then we just have to multiply the power to the front, keep the brackets the same, reduce the power by 1, and then multiply by the derivative of the inside bit, the bit inside the brackets. Right, like I said, we've been doing chain rule all along, even for a question like this that we did at the start. It's still the chain rule. Here we go. The bit in the brackets is x. Therefore, the power goes to the front. We reduce the power by 1 and multiply by the derivative of x, which is just 1, so we never bother writing that times by 1. But it's still the chain rule. Right, using our formula sheet, there's other rules we can do. First of all, the derivative of natural log of x goes to 1 over x. We're going to apply that, plus we're still going to be using the chain rule. So here's an example. Natural log of 2x. Well, the bit in the brackets is the 2x. So we're going to differentiate by going 1 over the bit in the brackets. That won't change. But then we multiply by the derivative of the brackets, which is 2. We can simplify this and get 1 over x. Another example will make the bit in the brackets a little bit more complicated. But this is still the inside function. So once again, chain rule says we differentiate the outside bit. So just differentiating the natural log goes to 1 over the bit in the brackets, which is all of this. We don't need to change this. But then we multiply by the derivative, and since it's got multiple terms, we'll put it in brackets. We multiply by the derivative of all of that. And we can just write that as a single fraction. We don't need to write it as 2 separate parts like this. Alright, have a go at this one, pause the video, and see how you go. Right, here's the answer. 7, that just stays at the front, times 1 over x squared, multiplied by the derivative of x squared, which is 2x. Simplifies to this. And we can simplify this further by dividing both sides by x, top and bottom. Right, let's move on to another one. What about the exponential e to the power of? That differentiates to itself, so that's nice and easy. Now if we just apply the chain rule to this as well, we're going to get the same thing. The bit in the power just doesn't change. And we just have to apply the chain rule part, which is to derive the bit in the brackets and multiply it. So it's just 2 times. Once again, a slightly trickier example. But the good thing about e is that it differentiates to itself. So here it is again. But we have to multiply. Even though this bit stays the same, we have to multiply by the derivative of it, which is 10x minus 7. Right, and one for you to try. Here we go, see if you can differentiate this. Pause the video and then give it a shot. Right, here we go. This whole bit doesn't change because it's an exponential, but we multiply by the derivative of that bit. And we can simplify by multiplying these two terms together. Usually simplification is not required for an achieved question, but here you go anyway. Right, let's look at a trig function. These all operate the same if you can see the formulas here, if you can see how you differentiate sine, how to differentiate tan, etc. So first of all, differentiate the outside bit, sine goes to cos, and then we multiply by the derivative of that 2x. Simple as that. Right. Another example, not using sine, but rather using sec. Sec differentiates to sec times tan. So we'll have to apply that first. Sec of the brackets goes to sec of the brackets times tan of the brackets. This bit does not change once again. That stays all the same. But then we just have to multiply by the derivative of this bit in the brackets. And put it in brackets itself. Alright, and one for you to try. We'll try cot of this, and I'll put a 7 at the front. Pause the video, see how you go with this one. Here we go, so that 7, that just stays there, it's just a coefficient. Cot goes to negative cosec, so we'll put the negative there. The bit in the brackets does not change because it's the chain rule. Then we multiply by the derivative of the bit in the brackets, which is this, and we can once again simplify if we wish to. It is not required, but here we go. Multiply those two bits and the cosec bit stays the same. Okay, the next rule, let's look at the product rule. Very similar to the chain rule. So here's what we did for the chain rule. This was a function f and a function g inside of it. Now we're going to look at a product of functions, in other words, two that are times by each other rather than one being on the inside. We still have to keep chain rule in mind though. So for example, f times g, and we won't use the times symbol, we'll use a dot instead, so we don't confuse it with x. So if y is a function of two separate bits times each other. So to differentiate this whole thing, this product, we cannot just differentiate each bit by itself. This does not work. Instead we have this. The derivative of f times g plus the derivative of g times f. Now, you may have noticed that I wrote it in a different order from the formula sheet, so here's how I write it. I prefer this formula, this version, because although it is actually identical, because the order when you add doesn't matter, so it's actually identical, writing it like this will be useful. See, the order in which you add doesn't matter. Writing it like this will be useful when we come on to the next rule. So we'll stick with this. So here's the formula. This is how we differentiate a product. So here's an example. We'll stick with polynomials for now. Of course, you could just multiply these two polynomials, and we'll do that to check our answer. But let's just practice the formula first. Alright, so let's identify f and g separately, so we can differentiate f separately, which is 18x squared, g separately, which is 8x. Now we'll apply our formula. to find the derivative of this. So of course we could just differentiate it bit by bit like this. There we go. Adding them together and just doing it as one big bit. But we're going to try the product rule now to see if it works. F prime times G plus G prime 8x times the original F. 72x to the power of 4 plus 48x to the power of 4, and this of course adds to 120x to the power of 4, which is the same we got by doing it the other way. Of course we need this rule for when you cannot just multiply two functions together. Let's look at an example of that then. So e to the x times sine x. You can't just multiply these two any further. You can't simplify this at all. So let's identify f separately and g separately, and we'll get the derivative of each bit. E to the x differentiates to e to the x. That's easy. Sine goes to cos. Now we can just apply our product rule. The derivative of y is equal to f prime times g plus g prime times f. This will do. Don't need to simplify it, but you can, since they both have an e to the x term, we can factor out e to the x. This will be useful for the merit questions, but unsimplified is perfectly fine. Another example. Let's try this one. Slightly more complicated, but not too bad. Just to keep us on our toes with our chain rule at the same time. Alright, so we've got f prime. Takes a little bit longer to figure out this one, but you can just, I recommend, write it on the right hand side of your page so you've got room to work it out. Same thing with g. G prime is this. Applying the chain rule, of course, always using the chain rule. I'll just move it over here so it's out the way so we can actually write an answer. Here we go. Just using the bits that we found on this side, one by one. And that's good enough. We don't need to simplify. We could. This bit is a common factor. And this will be helpful for some harder questions. But the top bit, unsimplified, is sufficient for an achieved. Alright, here's one for you to try. Pause the video, see how you go. So, first of all, identifying your first part of the product, differentiating it, simplifying if you can, that will help. And your G term, differentiate. And now just plug them in as the formula says. Here we go, f prime g plus g prime f, and that's done. We can simplify it if we want, but wasn't required. Here's another one for you to try. See if you can pause the video and have a go at this one as well. Alright, here we go. The derivative is going to be f differentiated to f prime. Of course, that goes to negative, so we'll put the negative at the front. G, use the chain rule. Have to squeeze this in a bit. Oh, forgot the power of 3. Simplify it a little bit. Alright, so there's our 4 terms that we're going to need. Now we just apply it. F prime, here it is, times G plus G prime and multiply it by the original F. Right, the next rule, the quotient rule, let's compare it to the product rule. So before we had a product of functions, now we're going to have a quotient, which is a fraction. And of course this means 2 parts that are now divided by each other. We still identify f and g the same way, except f will be the top bit and g will be the bottom. So here's the formula. You see how you need the f prime g bit first. So we'll identify f as the top bit, g is the bottom. We're going to differentiate it, and it is not just the same as this. So instead we're going to have to use the product rule, very similar, except we're going to put a minus, which is why I did it that way in the first place, and we're going to divide by g squared. So let's try this example we did before. We'll move g on the bottom, so you can see it's now a quotient instead of a product. We have to identify what is f, what is g. So g is that bit, f is this. We need our derivatives of f and our derivative of g. And now we just plug it into the formula. Slightly longer formula, but not more difficult. F prime g minus g prime f, divide the whole thing by g squared. And this can be simplified, although this is not required. The stuff in purple is beyond what's required for an achieve question, but it's always a good idea to give this a go. It will help for further on. All simplifies down nicely to just 302. Of course, we can check that by just simplifying it to begin with. However, this won't work for most questions. So we have to use the formula. Here's another one. A bit more complicated. Let's use not just polynomials. Sine 2x over e to the 6x. Identify f. Find f dash. Identify g. Find g dash. Apply the product rule next. And that will do. We could, of course, simplify that fraction, that bottom bit. So let's do that now. But this would be sufficient for an achieve mark. You'll notice they normally say you do not need to simplify. But we could factor out the e to that bit. And that can be useful, especially for later on. And we could apply the power rule to that e to the 6x squared. And this can be cancelled off as well. Right, so this is simplified, but that will do just fine. Right, let's use another example from one we did before. We'll change it into a product, from a product to a quotient, just to see how this all works. F is this bit on top, which differentiates to just 1 over x. We did this before. G is this bit on top, on the bottom rather, differentiates to 7e to the 7x. Let's go chuck it into our f prime g minus g prime f all over g squared. Alright, so f prime first. Here we go, just plugging into the formula, like we've done a few times now. All over, and we can simplify this to become 14x instead. But we don't have to. Right, once again, reminder, this is fine, but we should give simplifying a go anyway. If we can factor out an exponential term, that would be handy. If we leave it unsimplified, you can see how this cancels off more easily. So there we go. This is your simplified answer. Right, one for you to try. Pause the video, have a go for yourself. So, f is the top bit of the quotient, differentiates to this. G is the bottom bit, differentiates to this. Let's do our quotient rule. Very complicated, but you don't need to simplify for achieved. You don't need to expand this bracket either. That'll do. Okay, turning points. So turning points are these bits just here. But where it turns from going uphill to downhill or downhill to uphill. We identify these, of course, as maximums or minimums. And you can see at both these points, the gradient is 0 just for that instant, just at that point. And that's going to be the key to finding these points. So if we have a function, we want to find the turning point, we have to first differentiate it and then find where that derivative, also known as the gradient function, is x. So here's an example, just a polynomial to begin with. Whereabouts is the turning point for this? Differentiate it once. You get this function. Where is it equal to 0? We have to solve this for x. Well, of course, this is just, you've seen this before. This is a quadratic, so if we factorize it, we can solve that way. We know that x is equal to -6 or x is equal to 3. They are the two turning points, because these bits here, these are both turning points because these two x values give you a gradient function, f dash equals 0. So we've got this. All this, we just have to decide which one comes first. Is it a maximum first? And a minimum x equals 3? Or is it the other way around? Is it a minimum first? So we can do this. You can do this a couple of ways, where you can try some points close to the one we're interested in. So we should try 2 points close to -6. Like -6.01 and -5.99, and see if the gradient is negative on the left of it. If the gradient is negative just to the left a little bit and positive just to the right, then we have a minimum. Or, of course, if the gradient, if it's a little bit uphill just beforehand and a little bit downhill just after, we have a maximum. So we can try points just next to it to find out. Or we can try the second derivative test, which means just to differentiate our function another time, the second derivative. So if we differentiate it again, that's f dash dash or f double prime. if the second derivative is bigger than 0, it's a minimum. If the second derivative is less than 0, it's a maximum. So here, find the turning points of this function. Well, it's a product. It's a product of two functions, so we're going to have to do the product rule. Let's do that. It's f times g differentiated, so first of all, we have to differentiate it, of course, so we have to use the product rule. F prime, g, g prime. We'll write this all out. The derivative is equal to f prime g plus g prime f. Now, this would do, but it's probably nicer to simplify it a little bit. So we'll do that by factoring out e to the x. And it's going to be handy because e to the x, that bit there by itself at the front, that tells us something. E to the x is never 0. So that means the bit in the brackets has to be the key to understanding what x value makes the gradient equal to 0. The answer is therefore going to be when x is equal to 3 over 2. And it's the only turning point for this function. Right, find the coordinates of this turning point. Well, notice its coordinates, we're going to need an x and a y. X and y coordinates. So this is just a polynomial, so let's have a go. It's got the extra constraint, x has to be bigger than 0, of course. So, step 1, let's write it out. We don't want the square root, we want it as a power. That will differentiate to 2x to the negative a half minus 1. We have to find where is this equal to 0. Well, it's where 2x to the power of negative a half equals 1. If you want to just solve for this, just a little bit of algebra. X equals 4. Remember, x has to be bigger than 0 as a constraint. So we know that the turning point is when x equals to 4, so we just have to plug it back into the original function to get the y value. Y when x equals to 4 is 8, minus 4, plus 2, so y is equal to 6. So the coordinates of our turning point, read the question again to make sure the coordinates of our turning point are 4, 6. As we start to look at equations of tangents and normal lines, it's first important to note that every achieved question thus far has only asked for the gradient of the tangent, not the actual equation, but we'll go as far as writing the whole equation for this. Here's a demonstration equation. The graph is not necessary, but it will be helpful for explaining it. We're trying to find the equation of a tangent line at a given point. Let's say, for example, x is equal to 1. So if we've got a particular point on this curve, let's say it's there, that can be x equals 1. We're trying to find the straight line that touches at that point and is parallel at that point. So first we have to find the gradient of the tangent, which of course is the derivative at that point where it intersects. So we're going to be finding the derivative when x is equal to 1. So we'll differentiate our function first using the chain rule. Here it is. And I'll simplify it a little bit. Now all that's left to find the gradient is to substitute in that value x that we want and work it out what is the gradient at that point. And that will work out to be -8. So that's the gradient, and that's what we're asked for every achieved question so far. But if we wanted to work out the whole equation, the equation of the line, it could be either of these, for instance, lines, but we just need to find what the correct y-intercept is to make it fit. So if we're going to do that, we have to find out what the y value is of that x coordinate being equal to 1. So we're going to substitute x is equal to 1 back into the original equation to get the y coordinate of that point. And it's going to work out to give us, it's going to give us 2. So we know that our x and y coordinates are 1 and 2. And using that, we're just going to go to our equation of a straight line for a tangent. So a tangent is going to be a straight line, and that's going to have an equation y equals mx plus c. And m, of course, is the gradient of the tangent, which worked out to be -8. So now that's left is to plug this back into our original equation, into our straight line equation with our x and y values and the -8, and solve to find that c in this case is equal to 10. So that means our equation of our tangent is going to be -8x plus 10. Right, so this is the equation of a tangent line. How do we find the equation of a normal line? It is a very similar process. So here's our original equation again. We're going to go with the same point, which is x is 1, y is 2 that we just found before. But in this case, instead of finding the tangent, we're going to find the normal, which is defined as just being perpendicular to the tangent. And to find the gradient for this, we can just use this property that the gradient of the tangent is related to the gradient of the normal by this. So if we have the gradient of the tangent, we can find the normal using this relationship. So using our -8 value we found before, we can find out that our gradient of our normal is going to just be therefore 1/8. And this would once again do for every achieved question, but if we want to keep going, we just got to plug it into our straight line equation using the same x and y values and solve now just for a different c value. And this is the equation therefore of our normal line at the same point. Right, here's one for you to try. Pause the video and have a go. Okay, we're going to find our x and y coordinates. We know the x value is given as 0. We'll find the y value soon. But first, just to find the gradient of the tangent, we need to differentiate. And to do that, we're going to need to use the quotient rule for this question. Here's our pieces that we're going to use. And g prime. And then we just plug it into the quotient rule formula to get our derivative. Here we have f prime g minus g prime f all over g squared, and we just have to evaluate this now at x equals 0. So we plug in 0 everywhere we have an x value, work it out, and that will be our gradient. So here we go. This all comes out to just a value of 2. So here's our gradient that has been found. We're going to need to plug it into y equals mx plus c. We know that m is going to be 2 now. Just using the original equation, we have to find the y value that matches x equals to 0. So it's going to give us just a simple value of 1. So that we know that when y is 1, x is 2, the gradient x is 0, the gradient is 2, and that will give us a c value of 1. Now a practice for you finding the equation of a normal. Pause the video, have a go. Right, the first thing we're going to have to do is find that gradient, because that's what's required for achieved. But we're going to have to find the gradient of the tangent first before we can find the normal. So to do that, of course, we differentiate. Just using the chain rule. Sine goes to cos, and cos goes to negative sine, and we're going to evaluate it at that given value of x equals pi over 4. So here we go, we'll fill in, if we see an x, we'll put in pi over 4 because that's our x coordinate. 6 cos pi over 4 times 2 is pi over 2. Same thing for the sine value. You can use your calculator to work out each of these individual values, or you can use your formula sheet. Cos goes to 0, and it'll become sine goes to 1. So we've got a gradient of -2 at this point. Now, of course, we want the gradient of the normal, and we have to apply that -1 over the gradient of the tangent rule to give us a half as our gradient of the normal. that will do for achieved, but if we want to keep going, we want to find the equation of the normal line. We have to fill in this y equals mx plus c, and to do that we have to find the y coordinate for pi over 4. Once again, we can just chuck it into the equation, use your calculator if you need to, and we'll get a y coordinate of 3. So using a y coordinate of 3 and pi over 4 for x coordinate, we're going to have to plug it into this y equals mx plus c. Here we go, and that's going to give us a bit of rearranging to find our c value. And we don't need to simplify that. C can be equal to 3 minus pi over 8. Let's just write out the equation one last time. The equation of our normal. And lastly, even though I didn't say I was going to cover at the start of the video, here's a couple of questions from previous exams which don't really fall into any of the categories that we've covered. They're rather just features of derivatives and graphs. So I'll just cover both of those now. So this first question is asking us, when is the derivative, which is also the gradient, equal to 0? So what points on this graph, you can just inspect at what points is the slope 0. So it's everywhere here, and it's this exact point just there as well. So we're going to say anywhere where x is less than 2, not equal to 2, just less than 2, because we can't include that point just there because it's not smooth, it's a bendy bit, and also where x is equal to 4 for only that instant. Next bit, concave up, that just means this like U shape, so anywhere it follows that U shape, which is all this bit here from x is bigger than 3 all the way to x is less than 6, but not those bits for the same reason as before, because it's not smooth, it's got a sharp bit and it's not continuous. The last bit says the limit as x approaches 7, not to be confused with the value of the function when x is equal to 7. We want the limit, so it's not the same as that. To find the limit, we just look at which way was the function heading when we get close to 7. So 7 is just there, we're heading towards it, and we're heading towards that point as well. And since we're going towards the same piece, we're going towards the same point as we got closer and closer. They're both heading towards the value of 3. So we can say that the limit of this function, since they're both heading towards 3, not to be confused with the actual value of the function, the limit for this function is 3. And here's the previous question. Same question to start with. When is the gradient equal to 0? Well, we can identify those points by looking at whereabouts is it flat. Whereabouts would a ball not roll? On the very top of that, or on this flat bit just here. So that's our two places where the value is, where the gradient is 0. So when x is equal to 2, but not this point here, not when x is equal to negative 2, because it doesn't actually have a slope of 0, because it doesn't have any, it's not smooth there. Also when x is bigger than 4, once again not including equal to 4, because at that exact point it's not what we call differentiable, which we'll cover in the next question. So when is it not differentiable? So we're looking for bits where it looks like this, where it's not smooth, it has a little jaggedy bit, or where it's not connected, or we've got a little hole in the middle of the function. We're looking for those three things. So here's a couple of examples. 3 places in fact. So when x is equal to 2 because it's not smooth, negative 2 sorry, when x is equal to 1 because it's not continuous, and when x is equal to 4 because once again it's not smooth. So it needs to be smooth and continuous, so no jaggedy bits, no holes, no jumps, for it to be differentiable. So that's the definition of that. And last question, once again, the limit. What is the limit of the function at x's as x approaches 1? What does it look like it's heading towards from the left? What does it look like it's heading towards from the right? Are they heading towards the same thing? Or is there a discrepancy between the two? And there is. They're not approaching the same thing from the right and from the left. Therefore we say that the limit does not exist. And these are the 2 examples of this in the achieve part. Usually this question is reserved for merit parts only. Right, that's the end of the video. Well done if you've made it this far, and if you haven't had a go at all those questions that are linked, I would recommend going through all of them so you can feel confident going into your exam. Good luck.